Welcome to the Deep Dive, where we take these complex, cutting-edge ideas, slice them into manageable, fascinating pieces, and hand you the intellectual shortcut you need.
Right.
If you want to be truly well-informed on the wild frontiers of science, you are absolutely in the right place.
And today we're strapping in for a journey that, well, it requires us to fundamentally rethink gravity, space-time, and existence itself.
No small task.
Not at all. We're discussing a hypothesis so radical it sounds like a pitch for an epic science fiction movie, yet it's deeply rooted in general relativity, quantum mechanics, and, maybe most astonishingly, recent observational data.
That's right. Our subject today is the cosmological idea that basically flips the known universe inside out.
Yeah.
What if our entire universe, everything we know, every star, every galaxy, the whole cosmos, is actually living inside a black hole? It's called black hole cosmology, or BHC.
And we've pulled a stack of sources for this deep dive. We're talking rigorous theoretical physics papers, some very complex cosmological model building that relies on quantum gravity corrections, and some really compelling reports on recent telescope findings.
So our mission today isn't just to describe this hypothesis, but to really understand its profound internal logic. We want to see how this seemingly outlandish idea provides alternative, and you could argue more elegant, solutions to some of the biggest unsolved mysteries plaguing the standard Big Bang model.
Well, you said it. Black hole cosmology isn't just one single model. You have to think of it as a robust class of scenarios where a daughter universe, that would be us, emerges from a black hole that's nestled inside a mother universe.
And that nesting idea is key.
It's crucial to the entire framework.
Okay, let's unpack this, because the main justification for even exploring BHC is that it naturally addresses these foundational problems that the standard model, it needs an added hypothetical fix for.
You mean cosmological inflation?
It's exactly inflation. BHC proposes these inherent mechanisms that just solve 4 core cosmological puzzles right out of the box.
Okay, so first up, we have the horizon problem.
Right.
Which basically asks why the universe is so astonishingly smooth and uniform across regions that, should never have had time to communicate with each other.
Second is the flatness problem. This really vexing observation that the universe's geometry is almost perfectly flat, which is a cosmologically unstable value that standard models. Well, they struggle to explain it without some extreme fine-tuning.
Then there's the structure formation problem. How did those initial tiny quantum jitters expand and freeze into the classical seeds that eventually grew into all the galaxies and clusters of galaxies we see today?
And finally, one of the biggest paradoxes in all of physics, the infamous black hole information loss problem.
The huge one.
It challenges the very foundations of quantum mechanics. BHC suggests a clean, conservation-friendly mechanism for information transfer, not destruction.
And the elegance of BHC, you see, lies in its ability to use the specific, really bizarre geometry of a black hole interior as the perfect stage for the birth and expansion of a new, internally consistent cosmos.
Okay, let's start there. Let's lay down the conceptual and geometric groundwork. So let's begin with that conceptual foundation. I mean, this isn't some flash-in-the-pan idea. It actually goes back to the early 1990s with pioneers like Lee Smolin, Pathria, and Frolov starting to explore what happens after collapse.
Smolin, in particular, introduced this really radical idea of cosmological natural selection.
The Darwin analogy.
Exactly. He used an analogy directly borrowed from Darwin's evolutionary theory, survival of the fittest, but applied to universes.
That's a huge shift in perspective. So instead of our universe being this unique one-off event, he's viewing it as just one iteration in an endless chain of cosmic reproduction.
Precisely. Smolin basically postulated that universes capable of forming black holes are inherently selected for survival.
Because black holes are the engine of reproduction.
They're the mechanism for it. If the physical constants in a parent universe, the mass of the electron, the strength of gravity, if they are tuned just right to allow for massive stars to collapse into black holes, that universe will spawn daughter universes.
And universes with constants that prevent black hole formation are cosmologically sterile.
They can't reproduce. They just die out.
So we exist in a universe whose constants are fit for life only because they were first fit for black hole formation. It provides this deep self-correcting mechanism for tuning physical constants over cosmic cycles.
Which is an incredible concept. It could explain why our constant seems so perfectly calibrated for stars and elements and, ultimately for us. But what makes this cosmic reproduction technically possible?
The geometry.
It boils down to a fundamental geometric trick that happens when matter crosses the event horizon and enters the interior of the black hole.
So let's dive into that core geometric flip. In the standard description of a non-rotating black hole, the Schwarzschild model, you have the exterior spacetime, and then the interior, which leads inexorably to the singularity at the center, R0.
Right.
But BHC models say, hold on, and they replace that singularity.
Correct. Or rather the theory, postulates that due to quantum gravity effects, that point of infinite density is removed. It's replaced by the beginning of a de Sitter universe, a rapidly expanding smooth geometry.
And this is where we get into the profound strangeness of general relativity, because the coordinates describing space and time for an outside observer, they completely switch roles inside the event horizon.
That's the key. Outside the black hole, in the standard metric equations, r is your space coordinate, your radius, and t is your time coordinate.
Simple enough.
But once you cross that event horizon, the radial coordinate r starts to act like time, and the time coordinate t acts like space.
Let's just pause on that for a second, because that is so counterintuitive, and it's the absolute key to this whole theory. If r becomes time,
it means you must inevitably move toward R0.
because time always moves forward.
Right. So inside the black hole, the geometric center must be your future.
It's not a place anymore, it's an event.
Precisely. Time flows inexorably toward the singularity, or in this case, toward the R0 surface that we've replaced with this quantum bounce point. So the location that was the geometric center for the mother universe becomes the initial time surface, T0, for an observer in the baby de Sitter universe.
It's a dimensional conversion. The radial direction of the parent universe collapses into the initial time point of the daughter universe.
And this leads to this critical concept we call the big convergence. Imagine matter falling into this black hole over vast stretches of time in the parent universe.
Millions, billions of years.
Exactly. Different eta values in the parent universe.
Okay, so all of that material, it doesn't matter when it fell in, it's all headed for the same geometric center, R0.
And because R0 is the initial time T0 in the new cosmos, all that infalling matter enters the baby universe at the exact same initial moment.
But at different places.
But at different locations, because the parent's time coordinate, T, has now become the daughter's space coordinate. So the material is distributed across this new, expanding de Sitter universe.
So the timeline of the parent universe, stretched over eons, is mapped instantaneously onto the geographical spread of the daughter universe. The longer the parent black hole exists,
the larger the spatial volume of the baby universe it creates.
That is a foundational conceptual leap. And it's what allows BHC to solve all these other problems.
Oh.
Right, speaking of all that material falling in, this conceptual setup offers probably the most elegant solution to what is, I think, physics' thorniest contradiction, the black hole information loss problem.
Yeah, this is a direct conflict between general relativity and quantum mechanics. It's been famously debated by giants like Stephen Hawking and Leonard Susskind.
And it starts simply enough, right? You have a massive star in a pure quantum state.
Meaning all the information about its constituent particles is perfectly known. Its entropy is zero.
Then the star collapses, forms a black hole, and this black hole, according to Hawking, radiates thermal energy away over vast periods of time.
And that's the crux of the problem. Hawking radiation is thermal, it's random, it's described by what we call a mixed quantum state. So if the black hole fully evaporates, all you're left with is this thermal radiation.
And the original pure state of the star, it's just gone.
It's evolved into a mixed state. The detailed information about the star's initial configuration, the history of every particle, has vanished.
Which quantum mechanics says is impossible. There's a fundamental rule called unitarity. Information must be conserved.
A pure state cannot evolve into a mixed state. It would violate the predictability of the quantum world. So if information is conserved, where did it go?
And the typical solutions get really complex. We're talking about firewalls or storing information on the event horizon, all sorts of speculative ideas.
But in the black hole universe scenario, the answer is just dramatically cleaner.
No.
The information wasn't destroyed, and it wasn't stored on the exterior horizon. It was simply transferred.
Into the new universe.
Exactly. The pure quantum state that collapsed into the black hole interior, instead of hitting a singularity, passes through this quantum bounce region. It emerges, maybe highly compressed and distorted, but it emerges as the initial, pure quantum state that defines the content of the newly formed universe.
So the black hole isn't a cosmic information shredder, which violates unitarity.
No.
It's a cosmic portal, ensuring that information is just conserved across this dimensional boundary.
The violation of quantum mechanics is avoided entirely. The black hole never truly disappears and takes the information with it. It just changes its geometric description from a collapsed object in a parent universe to an expanding spacetime for its new contained universe.
It becomes geodesically complete.
Matter and information are not destroyed, they're recycled.
Okay, so BHC fundamentally restructures the narrative of cosmic origin. We've got the geometry flip, the solution to the information paradox. Now let's look at how this structure provides these intrinsic geometric solutions for the major problems that, cosmological inflation was invented to fix.
That's right. The standard Big Bang model requires a period of extraordinarily rapid exponential expansion inflation within the first fraction of a second.
To solve the horizon and flatness problems.
Exactly. BHC bypasses this entirely. It solves these problems purely through the dynamics of gravitational collapse and the geometry matching that's just inherent to the black hole structure itself.
All right, let's define the horizon problem again, just for clarity. We look at the cosmic microwave background, the CMB, and it's almost perfectly smooth.
The temperature fluctuations are tiny, about 1 part in 100,000 across the entire sky.
And the problem is that two regions, 180 degrees apart in the sky, they should have been far outside each other's causal horizon at the time the CMB was emitted. They should never have had time to talk to each other, to equalize their temperatures.
Right. If microphysical forces can't travel fast enough to homogenize these distant regions, how did they get so uniform? Inflation solves this by expanding spacetime so quickly that widely separated regions were, in fact, incredibly close together before inflation started.
Okay, so how does BHC get the same result without that hyperexpansion?
The BHC solution is sort of twofold. It solves causality through the geometric flip we just talked about, and it solves homogeneity through thermalization during the collapse.
Okay, let's start with causality. How does the geometry flip ensure that causal contact?
Well, you have to recall that inside the black hole, the radial coordinate r becomes time.
Right.
Because of that geometric inversion, the forward light cone of any point right at the event horizon at T0 in the mother universe naturally encompasses all points along the radial direction in the new de Sitter universe.
So everything is causally connected at the start.
Everything. Since all the infalling matter arrives at T0 in the new universe, causality is just. It's built into that initial moment.
That's very elegant. The geometry itself pre-solves the connection issue. But that doesn't automatically mean the matter entering at TO0 is perfectly mixed and uniform, does it?
No, it doesn't.
I mean, if the parent universe had lumpy, heterogeneous gas falling in, wouldn't our universe be lumpy at the start?
That's an important and critical point. We absolutely need to ensure that the matter reaches thermal equilibrium before it enters the bounce. Now, if the parent universe is already highly homogeneous, then the daughter universe will be too.
But that's a big assumption.
It is. So BHC provides a more robust mechanism. The long, slow process of collapse provides the necessary time for homogenization.
Okay, let's unpack this using the detailed analysis physicists do on the paths of particles, the geodesics, as they fall in. We don't need the deep math, but the results tell us exactly where and when this homogenization happens.
We can analyze the path of particles in 3 critical regions defined by the Schwarzschild metric, looking at how much they orbit or interact before they hit the center.
Okay, region 1, far from the black hole. Large.
This is the classical Newtonian regime. Particles that enter this region, they don't just plunge straight in. Their orbits are bound. They circle the black hole numerous times, spiraling inward very slowly.
So they have time to mix.
Ample time. Millions of years in the parent universe's time frame. This allows the matter to interact, to thermalize, and to equilibrate with all the near-horizon material before the final plunge to the new T0. This is where the bulk of the required smoothness happens.
But wait a second. Isn't relying on matter circling around before it falls and just kicking the can down the road? Why should we assume the parent universe has been feeding the black hole exactly the right kind of smooth material for millions of years?
That's a fair point, and it's why the robustness of the model is tested by the internal physics. The key here is the duration of the process. Even if you have mildly lumpy material, given the vast timescales involved in these bound orbits near the event horizon, it's going to smooth out.
Through pressure and other forces.
Through pressure gradients, electromagnetic interaction, shear forces. Gravity is forcing everything towards the center, And any local lumpiness will be smeared out and thermalized over those long circling orbits.
So the black hole exterior acts like a massive cosmic blender, mixing the ingredients before they're poured into the new universe.
That's a great way to put it. But let's look at the other regions to be sure. Region 2 is just inside the event horizon.
At r equals 2 meters, roughly.
Right. Particles starting here are committed. Analysis shows they can still travel through a significant angle up to about 114 degrees before hitting the REO center. So some interaction happens, but it's not enough on its own.
And what about the deepest region, closest to where the singularity would be?
Here, the gravitational forces are so intense and the geometry is so warped that particles can't really bend enough to circle effectively. The maximum angle they can traverse is calculated to be around 80 degrees.
So that's not enough for global thermalization.
Not at all. So the conclusion is, as you said, a bit counterintuitive. The solution to the homogeneity problem doesn't come from interactions right at the center. It comes from the long, extended, spiraling process that matter takes before or just after crossing the event horizon.
And that extended time allows the matter to achieve the critical thermal equilibrium necessary for a smooth, uniform start to our universe.
Exactly. No cosmological inflation needed to iron out the wrinkles.
Next up is the flatness problem. We observed the density parameter omega to be incredibly close to 1.
Which means the universe is nearly perfectly flat.
And this is an unstable balancing act, right? If it were even slightly denser, the universe would have recollapsed shortly after the Big Bang. Slightly less dense, it would have expanded so fast that no structures could have formed.
In the language of cosmology, this is asking why the curvature parameter k in the FRW metric must be exactly k0, which is flat, rather than k1 closed or k1 open.
Now, inflation solves this by taking whatever curvature existed and just stretching it exponentially large.
Right. It makes any local observable patch look perfectly flat, just like inflating a small crinkled balloon turns a small patch of its surface into a flat sheet.
So BHC offers a fundamentally different solution. What is it?
It's based on geometric continuity. It's not about ironing out curvature. It's about topological necessity.
Meaning what exactly?
It means the interior black hole geometry has to smoothly match the exterior de Sitter geometry at the bounce point. And this requires that the spatial topology of both regions must be the same.
That seems like a really powerful constraint. So if the geometries must match, what does the black hole interior impose on the new universe?
Well, we have to calculate the spatial size of the daughter universe
Right.
from the perspective of the parent black hole's interior right at the beginning, at t0.
Yep.
When you apply that geometric transformation where the spatial coordinate r becomes time in the new universe, you are integrating the spatial dimension along a line of constant interior time.
And what does that mathematical integration tell us about the spatial size?
The calculation shows that the size tends to infinity as we move across the space, and critically, it tends to infinity linearly. The spatial slices inside the black hole are geometrically vast and structured in a very specific way.
So now we just checked the 3 possible geometries for the expanding de Sitter universe. Open, closed, or flat.
Exactly. We examine the scale factor for the de Sitter universe geometry, and we find that only one value of k causes the de Sitter spatial size integral to also approach infinity linearly,
It is.
the spatially flat solution KA0.
So the universe isn't flat because it was ironed out by inflation, but because it literally had to be flat to connect geometrically and continuously with the vast linear spatial slices of its parent black hole interior.
Yes. That is a profound difference. It reduces the solution space dramatically. BHC doesn't just allow for a flat universe. It requires matching to the spatially flat slices of de Sitter space.
So this topological necessity singles out the observed flat universe we see.
And it explains the flatness problem simply through geometric continuity, which is, far more satisfying than requiring extreme fine-tuning of initial conditions.
That's stunning. It means the shape of our universe was determined by the gravitational constraints of its cosmic incubator. Okay, let's move to the third problem. Structure formation. We know galaxies grew from tiny initial density perturbations, ripples, in the fabric of early spacetime. Inflationary models use quantum fluctuations stretched by exponential expansion to generate these seeds.
Right.
If BHC doesn't use standard inflation, where do our galaxy seeds come from?
In BHC, the source is elegantly connected to the parent black hole's decay process, Hawking radiation.
So the thermal emission that the parent black hole sends out into its own universe is also the source of structure in our baby universe.
Yes. The Hawking radiation is inherently quantum, and it appears as a spectrum of tiny quantum fluctuations within the newly formed, expanding de Sitter space inside the black hole.
This connects the macrostructure of our universe to the quantum mechanics of the parent black hole. But, why is Hawking radiation suitable for generating the necessary structure?
Well, cosmological observations, especially from the CMB, show that the density perturbations required to seed structure have to be nearly scale invariant.
Meaning the size of the fluctuation doesn't really impact its strength?
Exactly. And Hawking radiation, being thermal, generates a spectrum of fluctuations that naturally falls very close to this required scale invariant spectrum. It's an ideal starting point.
Okay, so we have the jitters. How do those tiny quantum jitters grow into the large classical density perturbations needed to seed structure?
This relies on a mechanism called classical amplification, which happens in any rapidly expanding early universe, including the de Sitter space that's generated by the bounce.
So as the baby universe expands, the wavelength of these quantum fluctuations stretches out.
It stretches rapidly, and the critical moment is when that wavelength outgrows the particle horizon.
The region that can be causally connected.
Precisely. Once the wavelength grows larger than the speed of light divided by the Hubble expansion rate, causality dictates that the fluctuation becomes frozen. The region the fluctuation spans is now larger than the region that physical forces can influence.
So it's locked in.
It is causally locked into a specific classical amplitude. Because no outside force can modify it, the quantum jitter essentially becomes a permanent classical ripple in space-time.
And those are the seeds.
Those are the frozen classical amplitudes that serve as the necessary density perturbations, the initial seeds of gravitational potential, which eventually collapse to form the great structures we see today: galaxies, clusters, and voids.
It's a neat, self-contained mechanism. The parent black hole's energy loss provides the seeds for the daughter universe's structure. So we have seen that the black hole cosmology model is geometrically and conceptually powerful. It solves major paradoxes just by assuming the black hole interior is the start of a new universe. But this entire theory hinges on one massive, non-classical assumption: that black holes don't actually contain singularities.
That's right. Classical general relativity, GR, predicts that once matter collapses past the horizon, it hits an unavoidable point of infinite density and curvature, the singularity.
Which is physically unrealistic, especially in a framework where information has to be conserved.
It is. So we have to move beyond GR. We have to invoke the currently unknown physics of quantum gravity, or QG.
Okay.
Any viable QG theory must, almost by definition, resolve singularities. It has to ensure that space-time is geodesically complete, meaning no physical object or information can simply vanish into an unphysical boundary.
And this is where the concept of the quantum gravity-induced bounce comes in. So instead of infinite density, what's happening in the heart of the black hole, how do quantum effects prevent that final crushing collapse?
The central assumption is that quantum effects establish a maximum or a critical density, which we can call rho critical.
Like a cosmic speed bump.
Exactly. It acts as a limit that prevents complete collapse and forces a reversal. This maximum density might be related to the Planck density, the theoretical maximum density allowed by physics.
How is this modeled mathematically? Is there an equation for it?
It's often modeled using what we call an effective density, which incorporates these quantum corrections. A common form is rho effective equals rho minus rho squared over rho critical.
Okay, that equation shows something vital. When the classical density, rho, is small, so far from the center, that correction term, the squared part, is negligible.
Right, and the effective density is just the classical density. Classical GR holds true.
But as the matter cloud collapses and rho approaches that critical density,
the squared term becomes increasingly significant, and it drives the effective density down. When rho exactly equals rho critical, the effective density, rho effective, hits 0.
And the collapse stops.
It's instantly halted and reverses course. The gravitational force flips from being attractive to being repulsive.
And you mentioned earlier that there's a compelling physical analogy for this, that it ties back to the fundamental resistance matter has to being squeezed.
Exactly. Some models suggest this critical limit is governed by the Pauli exclusion principle,
which forbids identical fermions like protons and neutrons from occupying the same quantum state at the same time.
Right. It's the fundamental quantum resistance to being squeezed indefinitely. When the density hits that critical point, You've hit the absolute maximum packing limit allowed by quantum mechanics, and the resulting quantum pressure acts as a force of repulsion.
It halts and reverses the gravitational collapse.
It does. So the Big Bounce isn't some exotic new field being introduced. It's just general relativity combined with basic quantum resistance, pushing back against infinite compression. It's a natural consequence of uniting gravity and matter laws.
Okay, to see this dynamically, physicists often use simplified but powerful models, like the Oppenheimer-Snyder dust cloud model.
Which describes a collapsing homogeneous sphere of matter.
So using these QG-modified equations, what happens during that collapse?
Well, the collapse halts not at a singularity, but at a finite maximum bounce density. And this occurs at a specific co-moving time, T-TePi-b, which marks the beginning of the new expansion.
Now, the critical engineering requirement for this whole process to work smoothly is the condition of the expansion rate at that exact moment, isn't it?
Absolutely. To guarantee a smooth transition from the collapsing phase, we can call that region I, to the expanding FRW phase, region 2, the expansion rate. The derivative of the scale factor, it must be exactly 0.
The zero velocity point.
Yes. If the velocity were non-zero, the geometric transition would involve an infinitely violent tear in space-time, which is unphysical. So the smooth matching is only possible if the collapse momentarily stops completely before it reverses.
Okay, now here's where it gets technically challenging, because observational data like those amazing images from the Event Horizon Telescope suggest that astrophysical black holes look perfectly classical from the outside.
They do. So the QG effects must stop the internal collapse without altering the classical Schwarzschild geometry outside the event horizon. That's region 3.
And the exterior has to remain classical, described by a constant mass.
But inside the horizon, we're using the QG corrected equations, where the effective density is used instead of the classical density. And this changes the effective mass of the internal matter cloud as it collapses and bounces.
So you have a changing effective mass on the inside and a constant classical mass on the outside. How do you match those two descriptions at the boundary?
This is the critical discontinuity. Matching the semi-classical interior to the constant mass classical exterior is difficult because the gravitational influence from the interior is mathematically different from what the classical exterior expects.
So how do you fix it?
To enforce continuity, to make the internal quantum dynamics look classical from the outside, physicists have to introduce a mathematical construct on the boundary shell.
And that construct is the effective stress energy tensor.
Exactly. And this tensor is not a physical substance. You can't go looking for it. It's a mathematical patching term. Its sole purpose is to account for that mass discrepancy. It acts like a source of energy and pressure that's mathematically required at the boundary to maintain the constant Schwarzschild mass on the exterior.
Even while the interior is undergoing a quantum-induced bounce. So if I understand correctly, the effective stress energy tensor is the mathematical price we pay for achieving two things at once.
What are those?
Resolving the singularity internally and ensuring the black hole looks perfectly standard and classical from the outside.
Precisely. It's the necessary boundary condition that allows the universe to be geodesically complete internally while maintaining consistency with our current observations of black holes externally.
So if the collapse halts and reverses, what does that new expanding phase look like from the inside? Does it just instantly become our present-day universe?
No, not at all. It first undergoes a rapid expansion phase. The region of maximum density and quantum repulsion, the core of the quantum black hole, naturally takes on the structure of a de Sitter space.
Which, again, is the mathematical description of a spatially expanding structure, exactly matching the structure of the universe during cosmological inflation.
Right. The QG corrections that stop the collapse are inherently repulsive, and that repulsion powers the rapid de Sitter expansion of the new universe. So cosmological inflation emerges naturally from the bounce mechanism itself.
Without needing to introduce some hypothetical dedicated inflaton field.
Exactly.
Now, to make this transition smooth, we have to deal with that coordinate flip again. We're moving from a collapsing geometry, where time is the radial direction, to an expanding geometry, where time is, well, time.
Matching a time-like surface, the Schwarzschild exterior, to a space-like surface, the expanding FRW interior, implies the light cone structure must literally change its orientation.
Light cone flip.
That's it. It means the speed of light and how it defines causality changes orientation across the boundary. This requires an intermediate region, an interpolating geometry, where the signature of spacetime smoothly transitions.
And how long does this internal inflation last?
Well, the internal expansion rate depends on the mass of the black hole, and
Ah,
we established earlier that the parent black hole is losing mass via Hawking radiation.
so as the black hole's mass weakens,
The internal gravitational field that drives the dissidal repulsion also weakens. This causes the internal inflation to decelerate and eventually stop.
which naturally solves the graceful exit problem that plagues standard inflationary models.
It does. So Hawking radiation acts in three distinct ways. It seeds structure, it drives the mass loss of the black hole, and that mass loss ultimately provides the mechanism for inflation to shut off, transitioning the baby universe into the slower, matter-dominated expansion we see today.
It's an incredibly neat convergence of mechanisms.
It is, and the ultimate fate, when the black hole eventually evaporates completely, is theorized to be the black hole unfolding into a white hole.
A purely theoretical object that expels matter instead of trapping it.
Yes, and this final, explosive expulsion would appear to the resulting universe as a Big Bang with a singular energetic past.
This has been a deeply detailed theoretical journey, confined largely to the mathematics of geodesics and curvature and effective density. But recently, the theory crossed a massive threshold. A startling concrete observation provided unexpected, potential empirical support for the black hole cosmology hypothesis.
We are referring to the analysis of distant galaxies using data from the James Webb Space Telescope, JWST, specifically the work done by physicist Lior Shamir concerning deep space galaxies.
What did the observations show that challenged the fundamental assumptions of cosmology?
Shamir analyzed 263 distant galaxies in the early universe, specifically focusing on those that were clear enough to assess their direction of rotation.
Okay.
Now, the fundamental assumption of modern cosmology is that the universe is isotropic. It's the same in all directions. It lacks a preferred axis.
So you'd expect a perfect or near-perfect 50-50 split between galaxies rotating clockwise and counterclockwise.
That was the expectation, but the data introduced a major statistically significant asymmetry.
How big of an asymmetry?
It revealed a significant imbalance. Approximately 60% of the observed galaxies were spinning in one direction versus the remaining 40% spinning in the opposite direction. Some initial runs even suggested the skew could be as high as 70%.
Wow. This challenges the core assumption of cosmic uniformity on the largest scales. If the universe has a preferred axis of rotation, it's not truly isotropic.
It's not.
So why is this asymmetry such a huge potential win for black hole cosmology?
Because it suggests the universe may have been born rotating. And BHC provides the simplest, most direct mechanism for imparting a universal spin.
Here's where it gets really interesting.
The models we've discussed so far primarily use the non-rotating Schwarzschild black hole. But if our universe emerged from a rotating black hole in the parent universe, a Kerr black hole, that black hole would possess a defined axis of rotation and angular momentum.
A spinning object begets a spinning universe.
Precisely. This preferred axis of the original cosmic parent would naturally influence the initial dynamics and structure of the newly forming universe. The angular momentum of the Kerr black hole would translate into a subtle rotational bias across the vast scales of the daughter universe.
Thereby creating the very asymmetry in galaxy rotation that JWST is now observing.
Right. So if the JWST data holds up under further scrutiny, that observed imbalance, that subtle universal spin, it acts like a geometric fingerprint left by our cosmic parent.
It would confirm the type of object we were born from.
And it makes BHC a potentially empirically testable framework, not just a mathematical exercise. It's the first potential observational evidence that the underlying geometry of the universe is not the standard perfectly isotropic Big Bang solution, but rather one dictated by a massive spinning object.
Okay, so a universe with a rotational bias isn't just a curiosity. It has profound practical consequences for how we measure and understand the cosmos. Beyond just explaining rotation, what are the other testable predictions of BHC?
Well, one key implication concerns geometry. While the topological argument for the flatness problem strongly suggested KO, perfectly flat,
Right.
the more recent rigorous quantum bounce models, the ones explicitly modeling the effective density transition, they naturally predict a small, non-zero amount of positive spatial curvature.
Meaning the universe isn't exactly flat, but slightly curved, like a massive, gentle sphere. even if the curvature is incredibly subtle.
Yes, K would be slightly greater than 0. And if future high-precision missions, like the European Space Agency's Euclid Observatory, confirm this small positive curvature, it would be a strong empirical indicator supporting the dynamics of a quantum gravitational bounce, rather than traditional inflation.
Which predicts perfect flatness.
Which predicts perfect flatness as a consequence of extreme stretching.
But let's return to the impact of confirmed rotation. If that rotational asymmetry is validated, the immediate consequence is a necessary recalibration of our deep space distance measurements.
Absolutely. If the universe has a rotational preference, then the standard cosmological principle that we can assume uniformity everywhere when calculating distances to supernovae and distant galaxies is fundamentally flawed.
Our calculations would be systematically biased.
They would. Our calculations for the deep universe, which rely on a smooth isotropic background, would be skewed by this rotational asymmetry. We would have to account for it.
And that recalibration could be the solution to cosmology's most notorious modern puzzle, the Hubble tension.
It could be. This tension is a growing and stubborn discrepancy. There are two primary ways we measure the current expansion rate of the universe, the Hubble constant.
From the early universe and the local universe.
Right. We measure the rate based on the early universe using data from the CMB, and we get one value. Then we measure the rate based on the local modern universe using standard candles like supernovae, and we get a significantly higher value.
And the two values just do not agree. The discrepancy is robust. It suggests that either our measurements are wrong or our entire standard model of cosmology is missing a critical piece of physics.
And recalibrating distance measurements for the deep universe based on a rotational axis. The bias introduced by BHC could potentially reconcile these two stubbornly different values. By systematically correcting for the anisotropy induced by the spin of our parent black hole, we might just bring the early and late measurements of the Hubble constant back into alignment.
That is an enormous cascade of consequences. A radical hypothesis about our cosmic birth from a spinning black hole provides a mechanism.
Rotational asymmetry.
That explains a bizarre observation, the galaxy spin bias.
Which in turn provides the necessary corrective factor, recalibration.
To potentially resolve the single most vexing puzzle in modern astronomy, the Hubble tension. That's one mechanism potentially solving 4 or 5 foundational problems.
It really shows the power of challenging foundational assumptions. By replacing the Big Bang singularity with the concept of a cyclical nested geometry, we gain a unified framework for solving problems that previously required separate and often clumsy fixes.
This deep dive has taken us on an exploration to the very boundaries of known physics, charting the possibility that our entire universe is housed within the collapsed but non-singular interior of a black hole in a parent universe.
We detailed how black hole cosmology naturally and, you could say, elegantly resolves the horizon and flatness problems through geometric continuity and the unique dynamics of geodesic collapse.
And it offers a clean transfer solution for the black hole information loss problem, avoiding the violation of quantum mechanics entirely.
And most compellingly, the theory provides a profound physical link between the geometric necessity of our birth and the startling asymmetry recently observed in distant galaxy rotation.
The possibility that we are a daughter universe born from a massive spinning Kerr black hole is now an empirically supported idea.
So what does this all mean for our perception of cosmic origin? Well, the BHC framework suggests we are not witnessing the universe starting from absolute, inexplicable nothingness. Instead, it posits that we are the inevitable continuation of a cosmic cycle.
A nested, self-reproducing structure.
Exactly. Where the collapse of massive stars and the formation of black holes are the primary recurring engines of cosmic reproduction.
So knowledge isn't lost at the event horizon, it's recycled. Matter isn't destroyed at the singularity. It's reborn in a new, expanding spacetime.
Which leads to our final provocative thought for you to mull over. If the formation of black holes is the universal reproductive mechanism, and if our daughter universe follows the same physics principles as the mother universe, does this not suggest a vast, potentially infinite chain of nested universes? Is reality, at its deepest level, fundamentally fractal?
Thank you for diving deep with us.